So, good day. Today I will discuss about our project 1, which is the decoder circuit. So, the goal of this project is to show the representations of octal, hexadecimal, and BCD in these 7 segment displays. So, in a 7 segment display, there are 7 segments, which is segment A, this one, segment B, segment C, segment D, segment E, segment F, and segment G. So as you can see here, we have A, B, C, D, E, F, and G, and these segments are powered each by a logic circuit or logic diagram. And this logic diagram is powered by a four input. So we have A for input A, input B, input C, and input D. So first of all, to achieve this whole circuitry, we nayagi pataog ka ng solution. So we have here 4 octal. So this is the truth table or the key mapping for the octal. So as you all know, an octal with an input from 8 and above will be 0. So we included only the input for 0, 1, 2, 3, 4, 5, 6, and 7, since 8 and above is already 0. So using key mapping method, we arrive with this equation. And using Boolean algebra, the final equation for segment A for octal is this. So we have y octal segment A is this output. The next, you have segment B for octal, segment C, which is this one, segment D, segment E, and segment F, segment G. So next 4 is hexadecimal. So hexadecimal is up to input of 15. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Then as we all know, this is an input of the octal. So we have at the our expression as the y of hex of A is equal to this one is the output of the octal at segment A. Then this expression is derived from the key mapping of this section. And then using Boolean algebra, we came up with this equation. And we have segment B, C, D, segment E, F, and G. Also, for the binary coded decimal, we only have an input from 0 to 9. Having input of 10 and above will result to 0. So we have here 1, 2, 3, 4, 5, 6, 7, 8. I mean 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 0 meaning 10 up to input of 15 is all zeros. So the same with the hexadecimal. This part is an octal, so we only needed to add this part. So we have segment A for the BCD. We have this one, segment B, C, segment D, segment E, F, and G. Then, so before having the circuit with the use of ICs, we first go with this, with having all the logic gates. So this part is for the octal. So as you can see, the output of the octal is used in the hexadecimal and in the BCD part. So simulating this from 0, we have 0. You have 0 input. Next is a 1 input and 2, 3, 4, then 5, 6, 7, and we have 8. So in 8, as you can see, there is already no output at the octal. 9, then we go to 10. So as you can see, at 10, BCD has already no output, and 10 in hexadecimal is equal to A, 11 is B, then 12 is C, 13 is D, 14 is E, and 15 is F. So in actual situation, we cannot use only this kind of gates. These gates in actual life come in a form of IC. So in IC, we have this one. So this one is for the octal, this one is for the BCD, and this one is for the hexadecimal. So we have, so overall, this project made use of 1, 2, 3, 4, 5, 6, 8, 8 OR gates, or 8 OR IC, which is a 74LS32, and we have 1, 2, 3, 4, 5, 6. We have 6 AND gates, which are 74LS08 gates. We have 1 NOT gate, 74LS04. We have 2 NOR gates and 2 XOR gates. So all in all, the number of ICs used in this experiment is 19. So we have an input of 1, and then 2, 3, 4, 5, 6, 7, 8. So as you can see, the octal part is not having an output. 9, 10, or A, B, C, D, E, and F. So that would be all for this project.